Hello. We have already introduced Lorentz transformation and we showed what are the implications of Lorentz transformation and how space and time is compared between two observers. Today we want to talk about velocity. Velocity, remember, is rate of change of position with respect to time. So it's an interplay of both distance and time together, and how velocity is related or how velocity transforms between two observers. This is broadly called Poincare addition formula. Poincare velocity addition. And this is a generalization of what uh, we know as Galilean velocity addition. So let's go back and look at how velocity addition is done in Galileo's time. So we consider a, a road, a straight road, let's say, and on that we have an observer G who is not moving, so that represents ground. So let's say ground G, and at some point A at a time is a car moving with velocity VA, and this is the velocity of A with respect to the ground, and there is another car B moving with velocity B with respect to the ground. And how you will go about deriving the velocity addition formula is this is distance x a as measured with respect to g. This is of a with respect to g. This is the distance b with respect to a, and the total distance is x of b g. Clearly, geometrically, we know that x b g is equal to x b a plus x a g. We could also have two measurements. This could be with respect to an origin, and then you would say this is the change or the displacement of two events that leads to this relation. That's good. And from this point on, if we were doing Newtonian mechanics, you would divide this relation by delta t, and time being absolute, each term in this gets divided by time, and we don't worry about how time is related between different observers. And this immediately gives velocity b measured with respect to g is equal to velocity of b with respect to a plus velocity of a with respect to the ground. And that's the velocity addition formula in Galilean relativity. So that's Galilean velocity addition. I think I pronounced Galilean correct. Velocity addition. But how does this get? How do we get this relation for for Einsteinian relativity? The main caption here is that we cannot divide by delta t in all three terms because delta t is measured to be different by different observers. So we go back to, let's look at velocity addition or Lorentz transformation and see what we can decipher in there. Remember, when written as a matrix transformation, we have uh, the Lorentz transformation described by gamma 1, beta 1, gamma 1, beta 1, gamma 1, and gamma 1. Right? That's the that's a quantity which involves the velocities. Beta, remember, is, so beta here is V over C, and gamma is given in terms of beta, is 1 minus beta, square root of 1 over 1 minus beta square. So that's where the velocity sits in the Lorentz transformation. If we had two such transformation, we can consider products of two matrices. So that's gamma 2, beta 2, gamma 2, and this will be beta 2, gamma 2 times gamma 2. And in principle, this is the, if we were to say this is equal to gamma 1, 2, that's the velocity of one with respect to the second observer. These are the two velocities of the two observers because the matrix involves the velocities, and we can call this beta 1, 2, and that will be our velocity addition formula in terms of these matrices. And velocity itself will be given by the ratio of the off-diagonal term with respect to the diagonal term. So we can immediately get this by multiplying these two matrices. So we have gamma 1, gamma 2, times 1 plus beta 1, beta 2, and and the non-diagonal term here is gamma 1, gamma 2, beta 1 plus beta 2, and these quantities remain the same. It's a symmetric matrix. That's 1 plus beta 1, beta 2. So if we have to get the relative velocity, we need, if we're interested in beta 1, 2, that's the relative velocity. That's given by the ratio of the non-diagonal term, which is beta 1, 2, gamma 1, 2, over gamma 1, 2, right? These two cancel out, and that gives you the relative velocity. But on the right-hand side, this is obtained by the non-diagonal term being gamma 1, gamma 2, beta 1 plus beta 2. That's your off-diagonal term, and the diagonal term is gamma 1, gamma 2 times 1 plus beta 1, beta 2. Thus, the relative formula of the Einstein's relativity or relative velocity formula is, after cancelling out the gammas, is beta 1 plus beta 2 divided by 1 plus beta 1, beta 2. This is sign dependent. We're talking about velocity of 1 with respect to 2. If we were to do the other way, if by any chance one of them was moving in the opposite direction, accordingly the signs will should be taken care of. And that's velocity addition formula or the Poincare velocity addition formula for you. Thank you.